Hi, my name is Yombo. I'm an application engineer and a HandyProbe and MetraSCAN technical expert. This short video today is to help you guys do better demonstration of the MetraSCAN system. We know that all demonstrations are different, depend on the customer, on the market, on the country you're in, but also on the technical levels of your attendees, so you need to adapt your speech. But one part remains the same, which is the system presentation. This is the part where you are running the show. This is the part when you need to outline the advantages of the system, and this is what we're going to show you today in this video. So we hope this video is going to be useful to new salespeople to develop their speech when doing demonstration, but also to experienced salespeople to perfect the way they do it. Thank you. So I will start by introducing the main components of the system. First, the C-track. The C-track is a dual camera sensor using high quality optics and infrared light used to track reflective targets. It's the eyes of the system. It tracks both the MetraSCAN and the HandyProbe into the 3D space. Then we have the controller, which is mainly the brain of the system. It computes all the data from all the devices and sends the useful information to the computer. Then the MetraSCAN. The MetraSCAN is made of a known pattern of targets that helps the C-track to position the scanner through the 3D space. Then we have two cameras and two laser lines that are useful to recreate the surface. Then the HandyProbe, just like the MetraSCAN, is made of a known pattern of target recognized by the system, but this tool is used to take just single point into the 3D space. Targets. Targets is a key element of the system. It's made of a reflective material and is recognized by the C-track. So you place them on the part and it helps you create a dynamic environment. So with this, you can work in unstable environments. Then we have the calibration artifact for the MetraSCAN. So just like the other tools, there's a known pattern of targets so you can calibrate in unstable environment. And the features on it helps you calibrate both the positioning of the scanner but also the quality of the surface. Finally, we have the C-track calibration bar, which we'll talk a little bit more later. And now let's discuss about the technology concept behind the MetraSCAN, the triangulation. Triangulation is used two times with the MetraSCAN system. First is to position the scanner into the 3D space using the C-track, and then it's used when triangulating the laser reflection on the surface. So let me explain that over the C-track. So triangulation consists of finding points into the 3D space. In our case, the points we want to locate are the targets positioned on the MetraSCAN. So how we do that? First, we have a baseline, a known baseline, which is the C-track, which we know the length. And at the end of this baseline, we have the two endpoints, which are the two cameras. So every time we move the MetraSCAN in front of the C-track, we can get the angle formed by the first camera to the MetraSCAN and the angle formed by the second camera. So with all this information, we're able to position the MetraSCAN in a space. Also, the C-track works at 30 Hz, which means it's taking 30 measurements per second. So we really have a live tracking of the MetraSCAN position. So now let's look at the surface creation using the MetraSCAN. MetraSCAN is made of two lasers and two cameras. One camera working with one laser and the other one with the other laser. So what happens? Each laser is actually a laser plane, and when it hits the surface, it creates a line, and the cameras are looking at the deformation of those lines. So in this case, the known baseline is the distance between the laser and the camera. The first angle is known, is the angle formed by the baseline and the laser, which is fixed. When the relative position between the object and the scanner changes, the vision angle of the reflection changes as well, giving all the necessary information to construct the surface. So before measuring the part, I will create a dynamic referential. To do so, I will apply targets directly on the object. There's two types of targets that you can use. The first one are swivel, so they can rotate, and they have a magnetic base, so they can stick on any metal object. The other type of target is stickers. Those stickers can stick on any material. So with the targets on, now the system can compensate for any vibration or part displacement. To define the dynamic referential, I go directly in VX Elements. So all I have to do is launch the detection mode. I select the targets that I want to use, then I click Accept. So if you look on the top right side of the computer screen, you see the dynamic mode icon. You can also see how many targets the C-Track look at. So right now it's 9 over 9. So if I put my hands in front of one, you can see that the number drops to 8. So there's a live feedback of how many targets the C-Track sees at a time. So we are now ready to scan the part. Inside VX Element, we're going to adjust the settings of the scanner to fit to the color of the part. To do so, I'm going to click on Scanner Configuration and then on Auto Adjust. So all you have to do is aim at the part and hold the trigger of the scanner. You see that quickly the software is going to compute the right settings to fit the color of the part. Those settings are the shutter time and the laser power. So let's accept those settings. There's also a couple of different parameters of the scan that you can adjust, such as the resolution. Let's put the resolution to, let's say, 1.5 millimeters. And you can also adjust different parameters, such as remove isolated patches or decimate triangles, which are going to help you clean the data at the end. So we're ready to scan. We launch the scan mode, and all you have to do is hold the trigger of the scanner, aim at the part, and it's just like spray painting. It's pretty easy and pretty fast. And as you can see on the screen, there's a live rendering of what you're doing, so you can see how much of the part is scanned. So once we're done scanning, we're going to accept it, and VX Element is going to finalize the model using its strong algorithms, giving the best result on the market. VX Element, every time you change a filter, let's remove isolated patches, or if you change the resolution, is always going to recompute the surface using the raw data, which means the images from the scanner, which always give a good result. Also, what you see on the screen is a direct STL file. So unlike a lot of devices on the market that gives point cloud data that you need to reprocess to do your analysis, right now you directly have a STL. So let's visualize that using the wireframe option. So you can see on the screen that the surface is made of a lot of small triangles, which is the STL. So with this, what you can do is save the mesh. So you save your STL and you can export that into your metrology software to do your analysis, such as a color mapping. So now that we scan the inside of the part, let's say we want to scan the outside of it. So remember, we're using a dynamic referential, so we're using the targets on the part. Okay, so I don't need to realign it. Even though if I move the part, I still can scan. And you see there's not a second scan being created or a second layer being created by the software. It's all aligned thanks to the dynamic referential. Okay? So this is really important when you work on a shop floor. It reduces the errors that can be caused by a vibrating environment or even somebody hitting your setup. I will take this concept a little bit further with moving the C-Track. So if I move my C-Track on the side here and go back on the scanning part of it, you see I'm still aligned. Okay, so there's no need to realign the data. So one additional key feature of the system is the possibility to use the handy probe with the MetraSCAN. So I'm to the same session where I scan the part, and I'm going to launch the probing mode. Let's start with the top plane. So you can see into VX Elements that right now the probe is aligned with the data that we scanned earlier. And even though if I move the part, okay, and let's probe the inside circle. And the probe is still aligned, thanks to the target that we placed on the part. So if we look at the data, you see that both the plane and the circle are aligned to the scan data. So this is really important to save time when you want to work with both probing and scanning. But most important, you don't lose accuracy trying to align both data sets. I will now explain how to extend the volume of the seed track. Imagine that you need to measure features over a part that is larger than the volume of the seed track. In this case, we can take advantage of the dynamic referential to extend the working volume. To do so, you just need to add reflective target in the new area that needs to be measured, and then add this target into the existing referential. By doing this, the volume is extended very quickly and we are still into the dynamic mode. But of course, there needs to be a certain overlap between the initial position and the new position. The calibration of the C-track is done using the calibration bar. As mentioned earlier, this bar is a traceable certified artifact. So the calibration is done to check the system against a known standard to make sure that it is accurate. The calibration is done through a wizard that guides the user throughout the whole calibration. The user has simply to place the bar in front of the C-track and follow the XYZ position asked by VX Element software. This assisted method reduces the human error that could be induced in the calibration. The calibration of the MetraSCAN is as easy as the C-tracks. All you have to do is launch the calibration wizard by clicking on the calibration button. Like the C-track calibration, the scanner calibration is done through a wizard, which once again reduces the human error. You simply put the artifact in front of the C-track, and the distance meter tells you if you're at the right distance. The first step is to scan the sphere of the artifact at different heights. The second step is to scan it from different angles. Once you're done, the software automatically computes the images and gives you a feedback on the quality of the calibration. The MetraSCAN comes in two different models. The MetraSCAN 70 has a higher maximum resolution, but a shorter standoff distance, which makes it perfect for small to medium parts that need a high level of details. The MetraSCAN 210 comes with a lower maximum resolution, but a longer standoff distance and depth of field, which makes it perfect for big parts that need fast scanning. The volumetric accuracy of the system is computed using the average method, following the ASME B89 standard. But all this information is available in the brochure. The whole MetraSCAN technology is based on what we call true accuracy. Indeed, the system's unique dynamic referentials allows to isolate the vibration from the environment. The system also has temperature sensors that can compensate for temperature changes. Finally, the system features automatic alignment capability, reducing the user error. I will now show you the accuracy of the system and prove that even in an unstable environment, we still keep this accuracy. So what I have with me is a ball bar, which the length between the two spheres has been measured in a lab. Here the length is 521.007 millimeters. So first, what I'm going to do is detect the target that are placed on the bar. So into VX Elements, I'm going to click on Detect Targets, select the targets I want to use, and then Accept. I'm now ready to scan. So first, I'm going to scan the first sphere. Okay, and see, what is important is to have enough data, to have a good density of points to extract the sphere. And also, you want to take data all around. So then I'm going to do the same thing on the other side, but before I do, I'm going to move the bar to prove you that even if the system is unstable, so I move the bar, I'm going to now scan the second sphere. And the alignment is still the same thanks to the target that are placed on the bar. So once again, I want to acquire data all around. I take my time to have enough points. So once you have enough data, what we're going to do is stop the scan. And we're going to go inside the X element to extract the distance between the two spheres. Then I'm going to fit the sphere on the data. So I'm not going to use the data on the border of the scan because there's not enough density there. So I want to make sure to have a good density of points to fit my sphere. So I'm using only the top half. Doing the same thing for the other sphere, then create my distance between the two spheres. And now the distance is 520.9774, which is actually 30 microns off. So you see now that we're still inside the 85 microns accuracy that we certified, even though we moved the bar.